Hi, sir.
Thank you. Hello. Good afternoon.
Good afternoon. My name is Alvadona Marwin, and I'm from PG third semester, Mathematics Department. So my question today is, when an object approaches to the speed of light, its mass becomes infinite. So can you please tell me why?
Of course. So, in the same fashion that I just explained, we already know that, of course, because of the Lorentz transformation, so the Lorentz transformation actually has to follow some very specific rules, you see. So the space-time interval, which is what we keep constant in general relativity, this thing has to stay constant, is equal to this. And of course, c here means the speed of light, t is time, x, y, and z are the three space coordinates. And of course, this is just a small variation from regular Euclidean space. So then, what we can do is we can use what we call the Minkowski metric, which looks like this, to encode this information in a better format. So how does this have anything to do with that, of course? Well, it's very simple. All this is just you take dt, dx, dy, dz, and then you multiply the metric in the middle, and then you get the row vector dt, dx, dy, dz. And of course, you can do the maths by yourself, but all this does is simplify to this form. Oh, crap. Okay, so what we're actually going to do is use Gaussian coefficients, which is going to remove the speed of light or set it to 1 instead so that we can work in peace. And so now, all that's going to happen here is that this is just going to have to be equal to the regular metric weight. Oh yeah, so all that's going to happen here is that this has to be equal to, of course, just this space-time interval right over here, which means something very special, right? So what I'm going to do is I'm actually going to write this as this, which is an abbreviation for all of these, times the metric, which looks like this, times this, which is just a row vector instead. So that means it's the transpose. And this has to stay constant, right? So that means that once we apply the Lorentz transformation, just like so, let me just rewrite this. Why do I hear people giggling? So, if we reapply the Lorentz transformation, what we're going to get is something like this. Oh, this is in the wrong order. Of course, once you take the transpose of these, it's going to be in reversed order, which gives us something like this. And this has to be equal to the normal format, because of course everything has to be conserved, which leaves us with the special equation that this, the Lorentz transform times the Minkowski metric times the Lorentz transpose has to be equal to this. And of course, this is a very special class of matrices. And of course, all we do is, in two-dimensional coordinates at least, we set this to just be equal to some matrix with components A, B, D, F, for example, which means the transpose is going to be A, B, A, D, B, F. And of course, then we just solve for it using the regular Minkowski metric. Now in the 4 dimensions that real relativity uses gets a lot more complicated, so we usually just use computers, but this is a nice exemplary example. What did I just say? So then it turns out that what we get is going to be, end up being something in this format. It's going to be some constant, 0, 0, if I remember correctly. And then, oh wait, no, this is the identity. It's going to end up being something like this. And then, over here, we're going to get a proportionality constant, beta squared, actually, I believe. but whatever it is doesn't matter. The fact is, beta is going to be very important because it's equal to the square root of 1 minus v over c squared. And so, what we call the gamma factor is just 1 over this. So then, this gamma factor is responsible for dilating every single quantity. So that includes mass. Mass itself might seem like a scalar, but it itself has to be dilated too by this, because this is actually sort of dilating not mass in specific, but what we call the stress energy tensor, the mass energy tensor, this, which encodes all of the mass and energy in a 4x4 format, which essentially has a lot to do with the Maxwell's equations for electromagnetism. So, the point is, we multiply this proportionality constant by this, which is essentially what mass is. And so, that means that, in essence, we're multiplying mass by the regular mass times the speed of light. So the rest mass times, not the speed of light, oh my goodness, the gamma factor, which is this. And of course, as you said, why does it approach, why does mass approach infinity as velocity approaches c? Sorry, I think I'm dying of heat stroke. So, why is this true? Well, of course, if you look closely, you'll observe that beta is going to approach 0 as v approaches c, because, this is 1 minus v over c squared, so of course, if you plug in c, this is just going to give you 0, because c over c squared is going to be 1, you see it. So, since gamma is 1 over beta, then, as v approaches c, gamma is going to approach infinity, because of course, the denominator is getting smaller while the numerator stays the same, which means it's going to go up and up and up and approach infinity. So that's essentially a short answer for why mass approaches infinity. Thank you.
I should big round of applause, I think. This is a tough question, not for the Professor Bari only. I also think the students that who has raised such a question, beautiful questions, in front of all the parents, students sitting here is very appreciable. Yeah, now we have a question from the little kids. So go there and read out the question.
We have a child prodigy, Ronak Tanveer from class 1 Little Flower School. Tanveer, please ask your question.
Go there. I am there.
Oh, thank you. How old are you? How old is he? Why does he have a water bottle around his? Okay, what's the question?
My question is my question.
Guys,
Why is electric current considered a fundamental quantity?
Why is electric current is considered as fundamental quantity?
wow, that's a hard question.
Because
What?
because there is noted as charge per unit time. There are two quantity is involved in it.
Okay, that's a very good question. So essentially, what he's saying is that amps, or essentially current in general, uses the units coulombs per second, right? Or amps. So, this is using something that is already a fundamental unit itself. So, why isn't this considered a derived unit? Now, I think that's a very good question. And the reason is, I think that charge should be charge should be the SI unit, but of course, the international standards have decided that coulombs themselves are not a derived quantity. Coulombs are completely original. And of course, there's been a big debate in the SI standard, in the standard international community about whether charge or current should be a standardized unit, but most people have said current. Now, I don't know why, because of course he raises a good point about this seemingly being a derived unit, so I'm going to have to think it over. This is the first question that I don't think I can answer. Okay, thank you.
Thank you very much. We are running out of time, so next question, please.
Next, we have Yasmin Nahar from Little Angel School. Please come over, please come over. When can, her question is when we can use conservation of momentum in daily life, please.
Hello. Myself Yasmin Nahar from Little Angel School. I am from class 9 and my question is when we can use conservation of momentum in daily life.
So the truth is, physics, especially conservation of momentum, is absolutely useless in my life is a lie. Okay, so conservation of momentum in terms of daily life, well, essentially conservation of momentum is applied in a lot of different ways. So for example, if you're a good 8-ball player or billiard ball player, I don't know what they call it, the pool, the game where you take a stick and whack the balls around into holes. That is the most glaring example of conservation of momentum, as once one ball hits another ball, this ball nearly completely stops, or it heads in another direction due to conservation of momentum, and the other one heads in the direction it was originally going. So this is the biggest example of conservation of momentum that you can find in your daily life. But of course, there are a lot of others. For example, there's a very big reason that you don't want to crash a car. Why? Because of conservation of momentum. The car is going to stop moving as soon as it hits the tree, but you won't stop moving. So you're going to fly right through the windshield and hit the tree in the face. So this is exactly why you don't want to crash a car. And in the same vein, you don't want to press both brakes on a bicycle at once, because you're going to keep moving, but the bike isn't. So your willy is going to go right into the bike, which is not a very good situation. So there are lots of places where you can apply conservation of momentum, and it's a very intuitive concept actually. And one more thing where you can apply conservation of momentum is airplanes. Now, lots of you may have wondered, especially if you're little kids, well, why don't airplanes just launch, stay in the air, and then wait for wherever they're going to rotate under them so that they can fly back down? And the reason is actually conservation of angular momentum, which is basically the same thing as conservation of momentum. And so, why is that? Well, the reason is, technically, you could do this, but it would cost way too much energy. It would cost so much more energy than using the angular momentum of the Earth to take off and actually go to your destination. Instead of that, what people are proposing you do is fly up into the air and exert a massive force this way to prevent the conservation of angular momentum from working. And of course, this also goes for rockets and so many more things. So in daily life, there are a few uses that you can already see that come from intuition, but if you actually go into a job where this is needed, like engineering, you'll see a lot more uses. So thank you.
Thank you.
Of course.